Hello, discrete math fans. We're going to talk about unique factorization. The most important statement about divisibility of integers comes up in the unique factorization theorem. It tells us that there's really only one way of factoring a positive integer into prime numbers. As an example, let's suppose we wanted to factor 756. Now we know that 756 can be written as 2 times 2 times 3 times 3 times 7. If you multiply this out, you'll see that. Now we could also write that 756 is 3 times 2 times 7 times 3 times 3 times 2 by rearranging the factors. And there are other ways of writing a factorization of 756. For instance, we could do 1 times 4 times 3 times 3 times 3 times 7. We could do 1 times 1 times 1 times 108 times 7. All of these work as factorizations of 756. Even with that in mind, we're going to say that there's really only one factorization of 756. First thing, we only want to consider factorization into primes. So let's not allow factors like 1 or 4 or 108. 108 is not a prime factor because that can be factored down further into primes. 4, the same thing. 4 is 2 times 2. 1 is not a prime number. And the other thing we're going to do is we're not going to consider a rearrangement of the primes to be a different factorization. So even though you could reorder your prime numbers, we don't want that to be considered a different factorization. So that tells us the theorem that we're looking for. It's the fundamental theorem of arithmetic. And it says that given any n bigger than 1, there is a positive integer k and distinct prime numbers p1 through pk and positive integers e1 through ek such that n can be written as p1 raised to the e1 power times p2 raised to the e2 power and all the way down to pk to the ek power. This positive integer k tells us how many primes there are. The p1 through pk are the primes that show up in the factorization of n, and the integers e1 through ek, those are the exponents that go on the prime numbers. The other part of the theorem says that any other factorization of n as a product of prime numbers is going to be identical to this, except of course there's the possibility that we could reorder the primes, but remember we don't want to consider that to be a different factorization. Now we're going to give a very careful proof of the fundamental theorem of arithmetic later on. And we're going to define something called a standard factored form in which the primes are written in ascending order from left to right. So we'll make a definition to say that given any integer bigger than 1, the standard factored form of n is an expression of the same type, p1 to the e1 times p2 to the e2, and so on all the way down to pk to the ek. K is a positive integer. Again, it denotes the number of primes in the factorization. The p's are the primes and the e's are the exponents. And now in the standard factored form, we're going to insist that the primes are ascending. So p1 is smaller than p2, and pk is the biggest prime. So the primes go in ascending order. Okay, that's all for now.